me. Good evening, everybody.
Sir, you can start your session.
Yeah. Is my screen visible now?
Yeah, it's visible, sir.
So today we'll just discuss about one of the application areas and some of the experiments and research that I conducted about quantum machine learning and its applications in finance and why it is important. So we have some good results which proves that QML would also prove to be very much useful in finance area. This is the brief outline. So what is the objective of the talk? Then a little bit about QML, a little bit about what are QNNs, quantum neural networks. Then Penny Lane library by Xanadu. Then implementation details of the study that we did, results, and then conclusion and future results. So the aim of this study was to develop a clear understanding of the promises and limitations of current quantum algorithms for machine learning specific to finance. So in this, we will use so-called quantum neural networks, which are basically nothing but parameterized quantum circuits. And we will use them to address a machine learning problem, which is like a price prediction or a continuous variable prediction in finance. We chose finance because this is much more relevant. The continuous variable price prediction or continuous variable prediction is a very common, very cumbersome task in classical machine learning for finance. So we thought we will look at it from the quantum machine learning angle. For this experiment research that we did, we used the Boston housing data, which is freely available data, and it has property prices from Boston housing, and it is the library is maintained by Carnegie Mellon University. If you Google Boston housing pricing data, you will find the URL. It is freely available data. What is quantum machine learning? So quantum machine learning can be broadly categorized into four classes. So one is, and depending upon the problem or the data, whether the data is classical or whether the data is quantum, or algorithm that is being used, or the quantum processor or the processor that is being used, whether the algorithm or processor is classical or algorithm or processor is quantum. So CC indicates let's say first C indicates the data and the next C indicates the algorithm. So CC indicates both are classical, which is the normal machine learning. Then the second box, you can see the data is classical and the algorithm or processor is quantum. This is, and then third you can see is data is quantum, and second you can see the processor is classical. So I'll come to the examples of each of these. Fourth case, you can see both the data and the processor is quantum. The first case is, I mean, you might be familiar of machine learning is this more common case where the data and the CPU both are classical, like normal regression problems, classification problems, etc. In the second case, what is being done is the classical data is being subjected to a quantum algorithm or quantum processor to see wherein we can have quantum advantage. The third case, the data is quantum, but the processor or algorithm is classical. The example of this could be error prediction data or quantum many body physics data, wherein the quantum data is being analyzed onto classical devices. This doesn't entail to be looking after much of a quantum advantage. It's just that this criteria could help to make better quantum computers, maybe due to with the analysis of their operations and the errors that they have. The third case is quantum, wherein the data and the processor both are quantum, which is quite rare case in present times. And some examples could be the study of quantum data, quantum algorithms, or quantum entanglement, or quantum error corrections onto the quantum processor itself. The most commonly, the most famous one is quantum data, classical data and quantum processor, because in many of the classical machine learning problems, we have the issue of high dimensionality, or we are not able to process.
So your screen is not visible.
What is it? Let me once again share it again. Is it visible now?
Yes, sir.
Yes, sir, visible.
Something is wrong. It might have vanished again, right?
Yeah.
One second. Getting some issue with my. Sorry. Is it visible now?
Yes, sir.
Yes, sir.
Yeah. So most popular approach of these is the wherein classical data is being subjected to quantum algorithms or quantum processors, because there are multiple issues in classical processing so far. I mean, in classical machine learning, there is a lot of issues regarding volume of data, regarding the number of parameters that is there, and it takes a lot of resources. So there is a need to find out better and more speedy computational processes. That's why classical data with quantum process or quantum algorithm is the most favorite research area that is being sought after. Then what are quantum neural networks? So quantum neural networks are nothing but parameterized quantum circuits. So if you if you might have seen, so this figure denotes a quantum circuit, and in the leftmost it shows ket 0, These are the qubits, and u phi x denotes a function or the some gates, some combination of gates. So what happens is in these gates, so these gates are different types. So there are some amplitude modification gates, some angle manipulation gates, C naught gates, Hadamard gate, superposition. So the gates which have angles with them, Rx theta, Ry theta, the poly theta parameterized gates, these gates have the angle parameterized, which means that we can change the angle. So you can think of it as a machine learning model. What is happening is this circuit will represent a uh, equation, or what generally people call is a model, machine learning model. So the parameters are the tunable parameters. So what will happen is in the left, the qubits that is being denoted, these qubits will not be zero initially. They will be data that we need, and the data will be encoded into them with different encoding techniques, and the data will be passed through the circuit. And uh, for the first time, we will initialize the circuit with random theta angle variables, and then we will take the expectation value as output, and we will match it with the uh, so you can say in classical machine learning we have a original variable y and a predicted variable y hat. So this expectation value over here out of the circuit can be considered as a y hat, and we will match it with the original uh, uh, target value, and we will calculate the gradient or the loss error. And with that we will using that we will find that how much off it is from the real value, and we will again update the theta values or the angle values to, and we will send these theta angle values again back to the circuit to run again. So this is how we will train the circuit. So this is basically what is a parameterized quantum circuit, and these are commonly now called as quantum neural networks, because if we see, they are very much analogous to the classical neural networks, in which different nodes are there, different data points are connected to different nodes, and different nodes have different weights and edges, which the weights will be there to be trained. Weights are the parameters, and the edges have bias parameters. All these parameters are trained, and these parameters are also analogous to the uh, rotation angles, amplitude parameters onto the circuit. So this is just a brief about PennyLane. PennyLane is a quantum machine learning library developed by Xanadu. It is syntax is just like Python, and it supports hybrid quantum classical programming. It also supports frameworks like PyTorch, TensorFlow, Cascade, Circuit, Circ. Circ is by Google. TensorFlow Quantum is also by Google. So PennyLane actually seamlessly supports all of these. And as a matter of quantum processors, it supports pretty much all of the quantum processors available. For example, Amazon Bracket, IBM Quantum, Google Circ, Google Sycamore, Rigetti Forest, Microsoft Project Q. PennyLane is one of the biggest quantum machine learning library out there right now. It has most of the features. Qiskit is quantum computing library specific to machine learning. It has not many features compared to PennyLane. So that's Qiskit is a bigger library in terms of quantum computing, but specific to quantum machine learning, PennyLane has more features. So now we come to the implementation details of the research study that we did. So this is some details about the data set. So this is an old data set. It is for Boston suburbs, and it has target value is the mean meridian price of the houses, and it has 506 data samples and 13 variables, 13 features. So that was one of the reasons why we took this data set, because this is fairly small data set. Therefore, it can be run on present small quantum processors or simulators. So we split the data set like normal machine learning scenario, and we split the data set into trained and test data set with 70% train and 30% test. Now, since we were running this on simulator and on IBM Quantum, so on simulator we had a limitation of 10, 11 qubits, and on IBM Quantum we had a limitation of 5, 6 qubits. So what we did was we ran principal component analysis. This is a technique to determine which of the features out of 13, which of the features are more important. So principal component analysis is a classical algorithm which will run, and we can define so for example, we defined 95% accuracy rate as a cutoff, and using that we find that we need approximately 9 variables to get more than 95% accuracy in the data set for prediction of the target variable. So now we will use these 9 features or variables, and therefore we need 9 qubits. So these are the implementation details from PennyLane. So first of all, the encoding of the data is done by angle embedding, which is the angle encoding. Therefore, each data point, each feature is encoded into 1 qubit. Therefore, 9 features, we need 9 qubits. And so there are 3 types of generally used encodings, data encodings. One is basis encoding, wherein the data is encoded on a binary basis. Like for example, you have a number 32, and 32 has a decimal equivalent of say 1011 something. These 1011 each becomes a qubit. This is the simplest type of encoding, but it is also very cumbersome. I mean, a number 32 can take around 7-8 qubits to encode. The another type of encoding is angle encoding, wherein suppose the number was 32, it is converted into so 32 equal to sine theta. I'm giving an example, it's not exactly the same, but the sine theta equal to 32, and we find out the theta, and then we encode this theta into the qubit or the circuit. And the third kind of encoding is amplitude encoding. What happens is in each qubit can have multiple data points encoded. So suppose each 1 qubit has ket psi state, and it is denoted by alpha ket 0 plus beta ket 1. So this alpha and beta can be the amplitudes. And suppose we have a state with 9 amplitudes, alpha 1, alpha 2, alpha 3 till alpha 9, and therefore we can encode all these 9 attributes into 1 qubit itself. But this is the most complex one. Therefore, we did not use it. We for this, since the data set was simple, fairly small, we use the angle embedding. Then for the QNN layer, we use a strongly entangled layer, wherein all the qubits are strongly entangled with each other. So, I mean, since entanglement is a very large topic in itself, I'll not go into the details of what is entanglement and what means by strongly entangling. But for this, I mean, to explain simply, any circuit can be designed in a manner that it is fully entangled, which is also called a strongly entangled, or partially entangled, or circular entangled, or series entangled. depending upon the needs that you have or the circuit that you design. So we use simply strongly entangled, which is the easiest way to do it, but it is also most cumbersome. So here in the bottom, you can see a schematic of the high level diagram of the quantum neural network. So in the leftmost, you can see the x0, x1, x8, the 9 parameters input. Then there is entangling layer. Then there are some more circuit gates. And then we have outputs. The outputs are again continuous variable predictions, which are the prices of the house. Then we also created a very similar. So in quantum neural network, we had 3 layers. The first layer is a classical layer, the second layer is a quantum layer, and the third layer is also a classical layer. And for optimizing the use, normal stochastic gradient descent. So what we did was we first input the data into the classical layer. This classical layer will input the data onto the quantum circuit, encoding with angle encoding. Then the quantum circuit will pass through the strongly entangled circuits and gates. It will figure out some of the expectation values and outputs, and it will give the output to the another classical output layer, which will pass it to the stochastic gradient descent to be able to calculate the gradients, and these gradients will be passed on to the angle parameters of the circuit, and it will be given back into the circuit until it get good results. Then this is represented very high level representation of the classical neural network that we built to compare it with the quantum neural network. So to make it apple to apple comparison, we again use 3 layers, one input layer, hidden layer, and the output layer. The hidden layer is corresponding to the quantum layer in the previous hybrid neural network. And again, the optimizer and everything was the same. So this is one of the results, which is like, you can see the loss decay graph. So on the bottom line is the epoch. On the right hand side is the value of the loss error, mean squared error compared to the original value. In blue, it is the quantum mean squared error loss, the blue graph. The orange graph is a classical mean squared error. The green one is photonic. So we use this problem onto one of the photonic processor also. We designed a photonic circuit. I have not covered the photonic circuit in this talk because it's another big topic. But we did this study with a gate-based, silicon-based quantum processor and a photonic quantum processor also. So as you can see, the quantum mean square error loss is slightly better than the classical one. The loss converges quite early and a little bit much lower compared to the classical one. Now I will come to this figure first. So here we can see these are the predictions of the housing prices from the classical neural networks. So the red ones are the actual prices, the red dots. The red dots are actual prices of the houses for different data sets. And this is sampled from the whole data set. This is not the whole data set, but it's a sample, big sample from the complete data set. The red dots denote the actual prices. The blue dots denote the predicted prices by the classical neural network. As you can see, it is not a very good model. As you can see, in many places, the blue dots are not really corresponding to the pattern of the red dots. The model is just learning something, and most of the prices are in two ranges, 2 layers, like somewhere between 25 and 15 or something, right? Now we come back to the quantum hybrid neural network predictions. So again, these red dots are the real prices, and the green ones are the ones which were predicted by the quantum machine learning, quantum neural network hybrid model. As you can see, these are much more generalized. The predicted prices are following the pattern of the real prices much closer compared to the classical one. So you can see the classical one was pretty much learning very, very less. It is very binary kind of prices it is predicting, 2 levels mostly here, but we can see the quantum hybrid neural network with just one quantum circuit layer also predicted much better results in terms of generalization. And this is the actual power and prowess of the quantum neural networks. This comes from the entanglement and superposition of the variables in the circuit. So this and complete entanglement gives correlation to all the variables with each other, and this correlation is understood by the model and is used by the model much more effectively compared to the one that is in classical. In classical neural networks, the all the variables are not entangled or correlated with all the other variables. They are somewhat correlated, and some of the correlations are understood. But in a quantum machine learning model, even at a very small scale, we have just 9 qubits and less data with just 3 layers. That you can see the data is able to learn a lot more. I mean, the model is much more accurate compared to the classical one. Of course, for classical one, we can say that these are just 3 layers. If we make it 30 layers or we make it into different kind of variable optimization, we can make a better classical model, which will learn better. We have those techniques available today. But for apple to apple comparison, we did a small classical neural network, which was same in structure as the quantum neural network. Because quantum neural network right now, we cannot make 100 qubits or 20 layers because the quantum processors itself are very small. So we can say that even at the simpler scale, the quantum neural network did a very good job. Yeah. So these are the conclusions that even at the very small scale, the quantum neural network gave a very good job. And so as a future research, we can explore similar techniques in chemistry, try different photonic continuous variables, different NSATs. There are much more, there is a lot of more literature that has come up. So yeah, so I'll give a brief too about what all other problems are there in quantum computing or in finance area, which are not really quite easily solvable by classical methods in today's world, and what different big finance players are doing in that stage using quantum machine learning. So one example is Netherlands ABN AMRO Bank has done a collaboration with Delft University and for quantum key distribution for cryptography and secure communication. Then, as you know, quantum key distribution allows several users to connect with each other and exchange unique complex codes without without the threat of being broken. Then Barclays Bank is collaborating with IBM Quantum, and they have set up a high-speed transaction settlement system, which is much better than a classical system. So they are using quantum computers for settling up transactions, which means they are using certain kind of quantum communication and again quantum key distribution. Then JP Morgan is using IBM Quantum to simulate financial products. They are using IBM Quantum. They're collaborating with IBM Quantum to make a large portfolio optimization problem solved in much lesser time using quantum algorithms compared to the classical ones, which today, I mean, best known classical algorithms of big size portfolio take around weeks or months to optimize. Then again, there is another BBVA Spanish bank, which is collaborating with Spanish National Research Council for encryption and key distribution and communication. So there is another example of a very difficult problem for classical algorithms, which is called the currency arbitrage problem. So what happens is, whenever two banks or multiple banks talk to each other, they decide upon a currency exchange. Suppose RBI wants to do some kind of a currency exchange with Bank of London, so they will decide and discuss and decide upon a rate of that. Okay, these many dollars for these many rupees we will exchange. So similarly, there can be n so if there are n banks, there can be 2 to the power n combinations. Like So Bank of London is providing a certain kind of exchange rates to RBI, but Bank of Japan is providing another exchange rates to RBI. Similarly, another some XYZ bank is providing another exchange rate to RBI for the same currency exchange. There are multiple pathways to do that. So as we add one more bank, the problem increases exponentially. So there are algorithms which are, quantum algorithms which can solve this problem in polynomial time, and in classical it is exponential. So it's a quantum exponential advantage. So there are people in JP Morgan and many other financial institutions working on this problem also. This is quite related to the portfolio optimization problem, which can be mapped as a QBO problem. So these are some biggest players in quantum machine learning, quantum computing for finance. So Multiverse is a company. It is a Spain-based company. It works solely for quantum computing for finance, and they have done a lot of research work, and they have products also ready in all of these domains like portfolio optimization, anomaly detection, training of traders, registries, ALCO matching, capital allocation, credit scoring, and many more. So Multiverse is it can be said as one of the leaders in quantum computing for finance area. Now, another company is Zapata. Zapata also works on, so Zapata is primarily not very focused on quantum machine learning for finance. They are more of a quantum machine learning, quantum computing algorithm company, but they have a very much, the second biggest focus area of theirs is finance. So they have done a lot of work on this. Even in generative quantum machine learning like Boltzmann machines or generative adversarial networks, their quantum variations and tensor networks for bigger simulations. So these all Zapata has been doing. Then some more are there. One is called QC, where they have their products in, they have their, not really products, but they have some scalable, small scalable services in risk analysis, Monte Carlo simulations, demands, predictions, risk analysis, portfolio selection. Then there is another company, is also quite famous name in quantum computing, and they have pretty much a lot of exposure in finance, which is Cambridge Quantum Computing, based out of the UK, I think. In the bottom, you can see there are plenty more startups and institutions which are focusing on quantum computing and finance. And this is little outdated. There are maybe 10, 20 more companies that have been added in the past few months. So we discussed the continuous variable prediction, which is in classical machine learning, is the regression, basically, linear regression, all of these things. So there are more application areas wherein quantum machine learning can be very useful for finance. For example, like we discussed just now, asset pricing, how Boston housing prices is asset pricing, then multi-asset pricing, then volatility estimation, then classification techniques can be applied to binary options reduction. So binary options reductions is also a sub part of portfolio optimization. Then financial forecasting, credit scoring, all these are very difficult and very sought after areas in finance in general, because if you see a financial institution, if you consider a financial institution like JP Morgan or RBI, you will have millions of data sets, and you will have thousands and thousands of variables. So there it becomes very, very tricky for classical algorithms to produce results. They run their algorithm of hundreds of nodes cluster with getting results in week or month. And in finance, getting results in time very speedily is very critical, because if you want some result today but you are getting that result in a week or a month, it's pretty much useless in finance specifically, especially like fraud detection and stock market trading, exchange rates. These are very real-time scenarios, and all of these that I've listed over here have there some research papers, some work that has been done already at a small scale, obviously. I mean, at very small toy level problems like with 10 qubits, but the research work and those experiments say that this can be promising in the future when we have bigger quantum computers. And on the more AI part, the generative modeling can generate. So quantum machine learning also has very good strength in generative modeling. And so if you are aware, generative modeling is the key thing which is behind image generation, image recognition, video generation, video recognition. If you might have heard, in recent days, ChatGPT became very, very famous. So all the models most of the models that are behind ChatGPT are generative and reinforcement learning kind of models. These are more closer to actual AI. And since quantum computing has bigger, very, very vast, dimensionality scale. I mean, if you have n qubits, you can have any amount of dimensions. I mean, suppose you have in classical computers, if you have some processing power of x, and you can process only some x number of variables in parallel with so many etc. computers. But in quantum computers, this dimensionality problem is solved exponentially. Suppose we have 100 billion parameters model running on classical machines of thousands of nodes. In quantum computers, that can be run on maybe just, for example, maybe just 200, 500 qubits one machine also, because the Hilbert space in quantum processes, quantum circuits is the dimensionality is infinite. Like I mentioned earlier, amplitude encoding. With amplitude encoding, you can theoretically encode almost all the variables onto just one qubit also, which is not really practically possible, but theoretically it is. So, I mean, you can see the comparison wherein the processing capacity of quantum computers is far more superior to classical ones. Therefore, quantum computers are very, very much niche and close to the problems in chemistry, which is material science, which is also climate, life sciences, drug discovery. Any kind of molecular simulation application area is very, very close to quantum computing. And the other one is finance, because it has got lots and lots of data and lots of parameters. Yeah, that's it. I'm good for questions, doubts.
So a few questions has been given in the chat.
Sure. Let me look at the chart. Nice the chat. Yeah. Okay. Speaker is done. I would like to record you. So first question is, what's your second? So do you see the question? So first question is, what's your favorite classical optimizer for these circuits, and which is the most promising one? So it is a nice question, and this question is a very, very much so everybody is asking that question in the research community, and nobody really has an answer. Currently, what is the scenario? Currently, a lot of these classically tested, tried and tested optimizers are being used, which are pretty much like stochastic gradient descent or different kind of divergence, or you can say von Neumann entropy, or you can say Renai divergence, or you can say normal gradient descent, or different differentiation or integration techniques. All of these classical tested optimizers are being used. Why? One, because as of now, there is not a very good optimization technique available, optimizer available in a quantum domain, optimizer circuit in quantum. Second, optimizer uses a lot of data in a lot of steps. So those might not be a very good candidate for a quantum circuit. So that's why these are being optimizers are being used as a classical optimizer only. And so there is no favorite. It depends upon the problem at hand, mostly. It has been recorded, link share, chat. Why are you limited to 11? Pardon?
I just wanted to follow up on that question. So, what do you think of Bayesian optimizers?
Yes, they are being used. So mostly on the Bayesian learning problems mostly. And so look, like I said, there is no favorite of anybody. So it depends upon the problem. It depends upon the pros and cons of the problem. So the problem that we took, we did not really focus upon the optimizer because stochastic gradient descent is the best known in regression. So we just took it. So I mean, in our case, the optimizer was not a focal point. So, but if so, we are currently doing a research study in our company. We are working on thinking about quantum-based optimizers. So yeah, again, I mean, depends on the problem. You can any day use Bayesian optimizers also.
All right,
Why are
thank
you
you.
limited by 11 qubits? Normally, even with 8 GB RAM and without truncation, one can simulate about. No, this is not the case because if you go with 25 qubits, so we had around 500 plus data points, right? So this 500 plus data points will also go into the memory. So 500 into 11 qubits or 9 qubits, that kind of a scale we're looking at. So, and trust me, I've done that. I took all the 13 features and took all the data, and it went on for 2.5 hours, and it was taking a long time to converge. Uh, so that's why we tried all of that. So that's why we reduced the number of qubits a little bit so that the circuit can be optimized. Moreover, when you run so simulating also is so we ran this on an IBM quantum machine and on a Rigetti machine and on Xanadu's photonic quantum processor. Simulation you can still do with 25 qubits on a simulator with with the whole data set. It might take 3 hours to simulate, but we wanted to run it on an actual processor so that noise is also there in question. And I mean, in my opinion, a simulator is just a test run. Actual run should be on a quantum processor to see something actual, right? Or you should actually use a simulator which mimics the actual quantum processor, which induces some kind of noise also. Running on a plain simulator, I mean, it just helps you create the problem, but it does not give you a good picture because with the good picture comes with a noisy environment, noisy quantum processor or noisy simulator. Then you definitely will have to reduce the qubits or the amount of data. How many qubits can be selected for QAnon? There's no limit of anything. It depends upon the system that you have at hand. Like we mentioned in the earlier question, 25 qubits can be done on simulator. Then you can do, if you are using simulator, you can do 25 qubits on QAnon. If you have a Rigetti access, you can do around 38, 40 qubits. Depends upon the QAnon itself does not have any qubit logical limit. Like in neural networks, there is no limit of nodes or edges or layers. It's possible to approximate gradient to topic for another day. And so the approximate approximation there not upon coding the gradients. What is happening? Why it is flipping? So there's no message. There's no one deterministic circuit for encoding or gradients, etc. There's a lot of research being going on, and like I said earlier, in classical machine learning also there is no one neural network which fits everything. There are hundreds of neural networks. Even if you say CNN, each problem CNN or each image set CNN architecture can be different. It is not like that there is a CNN of n nodes and n layers being used everywhere. Each CNN can also be different. Each CNN can have different techniques like dropouts or removal and addition of layers. So they will, I mean, logically it is even incorrect to think about that there could be one circuit or one technique for anything. As regard the second question, I'm not completely sure. So then you have the PPT. Can this be used for Forex? Asking out of. So like I mentioned earlier, I mean, I don't fully understand the question, but what I think it is related to currency arbitration that I covered in the slide briefly. Yes, we can use quantum optimizers, but there are not very good quantum optimizers as of now. It is open research, and people are working on it. Linda can share. Thank you. Can we share your thoughts on different insights in the applications? So again, this different insights is a so for example, in classical machine learning also, you can have a neural network. You can have hundreds of neural networks for same application with a slight, with exactly the same performance also, with slightly differing performance also. Now suppose we have a neural network for us problem X. A person wants more accuracy, another person wants less error rate, which is not the same as more accuracy. Another, because it can be recall, precision, accuracy, there are different metrics. So based on these kind of needs, there can be different neural network configurations for a single problem also. So similarly, finding an NSAIDs, training an NSAIDs is again quite a trivial problem as of now. People are trying to narrow it down that okay, these are the best known or tried and tested and set of NSAIDs for this problem, but these are again evolving, highly evolving. In what way does quantum optimizer differ from a classical optimizer? It can differ in many ways. For example, so there is a class quantum optimizer. I think it's a quantum. I think it is a quantum Weatherstein or something. I don't really remember the name, but point is, so quantum circuits can give you superposition and can give you entanglement. This can make the optimizer much more faster with working on all the data points in parallel. But this is not true as of now. It is still an open research. Can you suggest on an unbalanced, suggest approach for an unbalanced data set? I mean, so we randomize the data, we normalize and randomize the data. So I feel that I mean, in any kind of machine learning problem, we prefer unbalanced data set because a balanced data set will not learn much more. It will overfit, right? Can you briefly explain the process of generative models in QML? I don't know how to explain it very briefly. So if you know about generative adversarial networks, for example, I can say, so there is a quantum counterpart of generative adversarial networks. There is a hybrid quantum counterpart of generative adversarial networks, wherein the generator is quantum and the discriminator is classical. So when you have both the generator and discriminator quantum, they perform quite well. But the encoding the data of the discriminator onto the quantum circuit is a big problem right now, at least. There is another version, which is a hybrid GAN, wherein a generator can be quantum, the discriminator can be classical. So here we reduce the problem of encoding the whole data into quantum circuit. We don't do it. We just give the data to the classical discriminator. In the generator, we just initialize it with the random latent space or random variables, and we take the output and match it with the discriminator, and we try to make the quantum circuit of the generator better. This approach, hybrid approach, wherein the discriminator is classical and the generator is quantum, gives very good results. We have done case study and research on that, and we have produced the publishable results on that also. This hybrid generator produces very good results because the generator is learning much more faster, much more generalizable. For example, you saw in the asset price prediction, the circuit model was generalizing much more. So herein the generator will generalize much more. We will not have an overhead of encoding all the data into the generator or something, because the discriminator is classical. So this is one approach that works quite well. Likewise, there are Boltzmann machines, quantum bond machines, tensor networks, and all the generative models have their small counterparts into quantum space. They are still in moving research. Some of them work for some problems, some of them do not really work good for some other problems. And we share the GPT fine, suggest some real-time datasets to work for credit scoring. And you can real-time datasets. Real-time datasets, I mean, in open space, you will not find a real-time. You will have to make it real-time somehow. right? Else you will have to contact some institution to give you batch real-time streaming API something. I think it was in Any other questions? So from the chat, I think I covered in all the questions. If I missed something, please let me know.
I have a question,
Yeah.
Prateek.
Sure.
So I have a small question in the nature of a clarification, basically. So you suggested that there is something called quantum neural networks. I am a little bit confused because you told that the quantum neural networks has some parameters, so you are likening it to a neural network. But a classical neural network also has the weights, right? So how is it different from actually a quantum neural network? I'm not sure about that point.
How is it different from a quantum neural network?
Yeah, because what is the
so the difference? So structurally it is the same. The difference is in the processing. So for that you will need to understand what is superposition and what is entanglement, and what are the gates doing. How do they operate? There you will find the difference.
Then what is the justification for calling a neural network? We can just call it a variational ansatz circuit, right?
No, it is not a variational ansatz. So variational ansatz has a different set of ansatz. It has different structure and it has different output values compared to the parameter. So first of all, quantum neural network is a fancy term. I myself do not call it. These are basically parameterized quantum circuits.
Confusing. Yeah, its nomenclature is a bit confusing.
Look, I have not made the nomenclature. Okay, I'm just using the nomenclature that other people have made. Maria Schul and Lloyd.
Yeah,
sure. So I have not made that nomenclature. That is a fancy term to myself also. So basically, these are parameterized. Everything is a parameterized quantum circuit. Some are variational, some are like QNN, some are like QBO, some are like different. But basically, they all are parameterized quantum circuits.
Yeah, they're all parameters. That's fine. That's perfectly fine. And
the difference lies. The difference lies in the output values. Some can have classification values, some can have expectation values, some can have different continuous variable values. The difference lies in the shape of the ansatz, the type of the ansatz, right? And all of this is still a very open and running active research area.
Yeah, they are all evolving by the day.
Nobody has a demarcation that these are the type of insights which should be called X, these are the type of insights should be called Y. All of that is evolving, correct. And it will take plenty of more years to do.
Yeah, definitely. It's a long-term issue. So no, I'm just saying it because a neural network has some resemblance to a biological neural network. So that's why the nomenclature
comes.
So if there's some
so don't look at the circuit as a circuit. If you see the circuit, if don't look at the picture of the circuit. You convert the gate into a node. You convert the parameter into a weight or another parameter into a bias. So then it is the same thing, right?
Ultimately,
what are the nodes?
Some function. Yeah, ultimately it's learning some
function of the inputs. So right? The circuit is analogous to a big function. The classical neural network is So if you want to do it schematically, you can convert a gate operation into a node. You can convert a theta operator into a weight, right? It is the same thing. It's just the way of representation is different. The key areas wherein quantum circuits can provide some advantage is in how the processing is done in parallel and with entanglement.
Yeah, the superposition thing and all those things. Yeah, that's fine.
Yes,
that's fine. And the second question
I'll suggest you should take a small circuit of 4 or 5 qubits, take some 4 or 5 gates, and solve it with hand with a paper and pencil. Then only you will have clarity.
Okay, fine. Yeah, thanks for the suggestion. Yeah. And another question was that you have already commented that the quantum network generalizes much better as regards to classical thing. So
not in every case. Not in every case.
In some cases, some cases, yeah. As regards the Boston housing data set, right? So I just wanted to comment. So if you have some theoretical studies regarding the generalizability, like the VC dimension we have for the classical neural networks, like the hypothesis class. So have you done some studies along those lines in the case of the quantum neural quantum circuits? That how is some some study of that sort? Yeah.
Yes, there are. So the generalizability of the circuit can be calculated mathematically. You can write API for that. So the generalizability of any kind of ansatz can be calculated. The entanglement degree, the entanglement power, the entanglement surface area law, all of these can be calculated mathematically. And I have done some of these, and there are papers for all of these available on arXiv. if you search.
Okay, so there are papers regarding those, right? The generalizability
Tons
of quantum
of
circuits,
those,
right?
tons of they can give you
Ah.
mathematical derivation of the generalizability. For example, there is some topic called barren plateaus, which is
Barren
existing
plateaus,
in
yeah,
classical
exactly.
also, and in it is a
Yes.
bigger problem in quantum machine learning. So you can by hand write down the equations and you'll immediately figure out how big a problem of barren plateau is.
Okay, fine.
So that's what I
Thanks,
suggest
thanks.
whenever I give these talks. No, if you are interested or passionate about certain topic, start writing that on paper, else you will not understand.
Yes, definitely. These are all theoretically they're all theoretical topics. So we need to do this by hand. Otherwise, there is no escape from that. Yeah. Thanks. Okay. Thank you. Yeah. Thanks for the nice talk.
So there is 2 more questions in the chat from Sangram sir and Nalini ma'am.
So one I see is, I am new to this field. What is quantum data? What is the nature of that data? Suggest some website for a health data set. So one question is, what is quantum data? For example, quantum. So that is very. So the quantum circuits generate some data. Quantum machines generate some data. So they are in parameters. There are different Josephson junctions. There are different electronics. All of those data. Some of those data can be referred to as quantum, which is actually generated by the quantum processor. For one example is the error data from the quantum processor. Then there are another set of data which is like quantum many body systems, some of the quantum chemical system, molecular simulation. Some of the data can also be termed as quantum data, which is specific to that quantum system. So health data set website, I do not recall right now, but if you Google, you will find plenty of them. Even AlphaFold whole code and the database that they have used is on GitHub and online. Even in Kaggle, there are hundreds of data sets. And there are PDB protein databases. Plenty of those data sets are there. I mean, there are millions of data sets. I don't remember some particular. These were the 2 questions, right?
No, Sangram sir has asked about the annealing devices, how it works when we map our QuIC problem to annealing.
Then how does the annealing device work if we just map our QuIC problem to the annealing native problem? So I am not sure about the QuIC problem to the. So what do you mean by QuIC problem to the annealing native problem? Is there a plugin somewhere in QuIC which just maps to the annealer? I doubt that though. If it is there, it could be just for the QUBO problem. So again, to the first question, what I'll say is annealing devices are very different than the gate-based. They do not have any gates or circuits. They work on a very meta-heuristical way. And the key principle behind annealers is QUBO. So what happens is, so in an annealer, what happens is, first of all, refined and efficient control of each qubit is not required. It is, like I said, meta-heuristic and way of putting the problem. And in annealer, what happens is the system is put through an annealing process, wherein you can say that if you say classical annealing, it is like heating the problem and suddenly cooling down the system so that it goes through an energy change. So a similar quantum process is there for quantum annealing for the annealer, and first of all, it is set into a ground state energy, and the problem is mapped to the qubits in a QUBO format, quadratic unbounded binary optimization format, wherein the problem variables are binary variables. I mean, if you want to go into the detail of QUBO, you can look at it. It's a, big topic. So those QUBO binary variables are mapped to the qubits on the annealer, and then annealer goes through the annealing process to find to stay in the ground state energy after time t. And at this time, the coefficients which are analogous to the variables or parameters of the system will be found out. The appropriate coefficients of each qubit, logical qubit, will give the parameter values, which will be your model. So like I said, it's a completely different technology compared to the gate-based ones, and annealer is very, very limited to certain types of problems only. References, you can just Google asset price prediction, quantum machine learning, and I'll suggest that best place to go through is Penny Lane demos. And you can also, I mean, the best way is the hardest way. There's no shortcut. In Penny Lane demos, you can find some of the information. And I'll say is if you're passionate enough, just go to archive and start searching the topic of your interest and read papers, read and read and read. And also, practice. Anyone thinking is spent as a parent over the high mutation what is random data discovered data. Yeah. Any other questions that I'm missing?
So you have answered all the things.
Cool. Great. Then we can disconnect.
Thank you.
Thanks a lot, everyone.
Thank you, Prateek sir, for the wonderful session. Through your session, we have got insights on quantum machine learning, quantum neural networks, and we have got an idea how it could be applied in portfolio optimization, fraud detection, as well as in credit scoring. Thank you so much for your valuable time.
Thank you. Thank you for having me. Have a nice evening, everyone.
Thank
Bye.
you. Thank you, sir.
Thank you. Bye.
Participants, I'll share you the recording in a drive and I'll share you the link.